Hey everybody, welcome to this lesson on operations management. In this video, we're going to be talking about statistical process control, which is a part of the overall quality management subject. SPC is really a quality management technique that we use to try and identify if things are working the way they should, or if things need to be, if machines need to be turned off and maintained. So it's basically a way of monitoring if processes are working the way that they were designed to work. What you see in front of you in this image is a control chart. The upper line, the green line up here, this is what we call an upper control limit, so UCL usually. And the bottom is a lower control limit, LCL. And then the middle is your average, it's your midpoint. And the basic concept here is that a process should stay within those upper and lower control limits. But if ever it goes outside of a control limit, that's a flag to, oh, something's wrong. We need to investigate. Now, why? What's the whole idea here? Well, in anything, there's always going to be some variation, right? Even if you were excellent at doing something. So, for example, let's say your job is you change tires on a car, right? You work in a garage, and your job is to change tires, and you're very good at it. And you got it down to an art, you've got it down to a science, and you're able to do it in 15 minutes. Let's say that's your average. Well, it doesn't mean that every single time you do it, it'll be done in 15 minutes. You might be able to do it in 12 minutes sometimes, in 16 minutes, in 13 minutes, in 17 minutes. There's always going to be some variation. You're not a robot after all, right? And even if you were a robot, there'd probably be a little bit of variation. So how do we distinguish between variation that is just normal, which we call random variation? Random variation is normal. And variation that is abnormal. Abnormal meaning that it's not random. There's a reason for it. Now that kind of assigned variation, we need to investigate, because it could be good or bad. Like if you have a point like this that went outside of the upper control limit, which means it took you so much longer that it was outside the range of what's normal, and we could say there's a reason for that to have happened. Everything in here is random, no reason, and that's fine. But there's a reason that happened. Or what if we had a point that came down below here? Well, that's pretty good, right? That's amazing. But again, we want to investigate. Why were you able to do it so fast on that one car? Was there a technique that you used that we should be, implementing across all of our workers? You understand? Like even variation that is good needs to be investigated for maybe for possible improvements. Maybe here you were using a tool that's probably not so good, and we don't want to be using that tool anymore. You guys get the sense of where I'm going with this? We're trying to separate random variation that is normal from variation that can be assigned to some reason. Okay, so we've got 4 control charts. 2 of them are quantitative. This is when you're looking at something quantitative, like a measurement. And 2 of them are qualitative, when you're looking at something qualitative, like an error, a defect. So let's get into it. The first one is the Xbar chart. Now, Xbar means a sample mean. So this is a control chart that we use when we're trying to monitor, right? When we're measuring an average something. So this could be a measurement, for example, a weight, an amount of time, something quantitative. And the control chart, if you've taken a stats class before, is basically just an interval, a confidence interval. Okay, we've done this in business stats. When we made confidence intervals, if this looks like, oh, I've seen this before, a PTSD or something, yeah, you have seen this before, guys. We did this in business stats. This is a confidence interval, and the upper and lower limits are basically just your intervals. Now, if you have a standard deviation, this is the formula you'll use. So if you're provided with a standard deviation in the question, then that's the formula. I've also given you the formula for the standard deviation. It's not likely you'll ever need to use it, but if ever you were asked to find the standard deviation, this is how you would do it. Otherwise, if you don't have the standard deviation, and I would say this one is far more likely to be the case, it just tends to come up more on exams, there's another way to find the Xbar chart to do your control limit, and that is using the range. Don't worry, I know it all looks like just a bunch of numbers or formulas. I'm going to explain to you how to use them. I'm just going to chat about them for a second. So this one is when we're trying to make sure that the average is, doing its thing. It's staying around where it needs to be. and there isn't some crazy high or crazy low averages. And then you've got the R chart. The R chart, the purpose of it is not to monitor the average, but instead to monitor the range. R stands for range. I'll give you an example of why this matters. Let's say you again are changing tires on a car, and we take, and the way that we usually use SPC is we'll take multiple samples and we'll inspect them. So let's say we had a sample where on day one, you changed 3 tires. The first one took you 15 minutes. The second one took you 14 minutes. And the third one took you 16 minutes. Well, the average, the X bar, if you averaged out those 3, would be 15. And the range, if you did the range, remember what range is. Max minus min, highest minus lowest. In this case, the range would be 2. So you look at this, you're like, okay, not bad. Pretty small range. The average is okay. Second day. Second day, you change 3 tires, 15 minutes, 8 minutes, 22 minutes. The average is still 15. Do the math on that. It's 15. But your range now is 8 to 22. Your range is 14. You see, the problem with only looking at the average is that it doesn't tell you the whole story. Look at this. Would you say that this is something that's working the way it should? No. But if you only looked at the average, you wouldn't tell. 15, 15. But then when you look at the range, it's like you realize, oh, something really weird happened in that second day. Like 2 out of 3 of these, not that one, but these 2 out of 3 of these were all messed up. That's why we have an R chart. We don't only need to monitor the mean, we also need to monitor the variation. And that's what the R chart is for. So, do you always need to do the R chart? The answer is no. Here's the thing. Listen up, because this is going to be important for knowing when to do it and when not to do it. If you have the standard deviation, then you no need for the R chart. If you have the standard deviation and you're solving your X-bar chart using the standard deviation, you do not need the R chart because the standard deviation is a measure of variation. But if you do not have the standard deviation and you're evaluating your process, whatever it is, using the X-bar chart with the range, you need to also use the R chart. So on an exam, they may or may not tell you that. They might just say, use the appropriate control charts, and it'll be up to you to decide, okay, I need to use the X-bar chart with the range because I don't have the standard deviation, but then that means I also need to do the R chart, okay? Good. Now let me show you guys everything I just said. So here's a question. We're going to do the first one. This is if you have the standard deviation, so let's read it. You've been hired by Domino's as a quality control specialist to ensure the consistency of pizza dough preparation across their franchise locations. As part of your role, you're tasked with implementing SPC to monitor the average weight of pizza dough. Using the data collected from 10 batches, and this is how we do it, guys. Here, you have 10 samples. This is not one sample of 10 pizza doughs. This is 10 batches of 6 pizza doughs. So that's the first thing you want to make sure you're good with. The sample size here is 6. The sample size refers to how many units are there in one sample. 6. You just have 10 samples. Please don't mix those up. That's maybe the most common mistake is students putting 10 instead of 6 as the sample size and then getting it wrong, of course. So we took 10 samples of 6. We want to construct 3 sigma control charts. And we know the standard deviation is 5. Perfect. So the formula is X-bar-R plus minus your z-score multiplied by your standard error. So X-bar-R is the average of the averages. So all of these values here, look, these are the average weights. These are the X-bars. You want to average out these 10 numbers, and that'll be your X-bar-R. Okay, so let's start there. Divided by 10. Okay, so my X-bar-R, my average of averages is 179.6. Okay, now for the z-score. The z-score that now is determined by the level of quality that you're trying to achieve. So it is most likely going to be stated in your question in this case, I've circled it where it says 3 sigma control chart. 3 sigma, that's your level of quality. The higher this number is, the higher the level of quality. And later on in this lesson, we'll talk about 6 sigma, which is the highest level of quality. 3 sigma is kind of your standard. So that's your z-score. So 3 multiplied by the standard deviation, which is 5, over the square root of your sample size, which is 6. .12. So 179.6 plus or minus 6.1237. And now we find our upper and our lower control limits. So do 179.6 minus 6.1237. The lower control limit is 173.48. And then if I add it, I get 185.72. So here is your control. Here are your control limits. This is what we'll use to build our control chart. Now, the way that you interpret these ranges depends on what it is that you're solving for. So because we're doing an X-bar chart, you look at your X bars to see if they fall within this range. X bars meaning your averages. So we go back and we look at the averages and we see, do all of these averages fall within this range? Let's take a look carefully. Anything below 173? No. Anything below 185? Oh, right there, 186. So as soon as you have even one point that is outside of your control charts, then you say the process is not in control. That's it. This process is not in control. There's something that needs to be investigated. Now, the next thing I want to show you is how do you take this and graph it. It's actually really straightforward. And it'll be the same idea for every control chart. So I'll show you how to do it with an X-bar chart, but it'll be the same thing whether it's a P chart, a C chart, or an R chart. So the type of chart tells you what your y-axis is. So because this is an X-bar chart, the y-axis is X-bar. Again, if this were a C chart, the y-axis would be C. And then your x-axis would be your samples. So we've got 6 samples. So 6 or 10? 10 samples. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now you have 3 lines. You have your upper limit, which is the 185.72. You have the lower limit, which is the 173. You have the midpoint, which is the X-bar. Those are going to be your 3 horizontal lines. And you want to make sure that you're also able to fit all of your X bars. So let's use red for the limit. So 185.72, put that up here. And 173.48, I'll just put that right here. I use green for my midpoint. All right. So I'm gonna do a little line break here because I'm not starting at 0. And I'm gonna enter my numbers here. I'll just write them out. 185.72. I had, oh, sorry, that's at the top. Oops. Right here. At the bottom, we have 173.48 or 173, yeah, 0.48. You write 0.5, it doesn't really matter. And then 179.6 is your mid. And then you're going to plot every one of your 10 points. So 175, for example, is sample 1. We'll put that right there. 180 is a little bit higher than that point. 178, just a touch lower. You see? You're going to plot all of your points. 186 is the one that put us outside of our control limits. 182, put that here. 179, just a hair below. 183, 177, 176, 180. Okay. And then we connect our dots. And that's it. That's your control chart. So I'm gonna connect each of these dots with a straight line. Oh, that's supposed to be straight. Let's try again. So if you are doing this on the exam, I suggest that you bring a ruler just so that you get some nice lines. I'm not worried so much about having everything be exactly to scale and be proportional, but if you can have some straight lines, it'll just make your answer look better, easier to read, easier to give you all the marks. There you go. Okay, so you can even circle the one that's outside if you want, totally up to you. But this is a control chart. This is what it looks like. Okay? Now, what if you don't have the standard deviation? This is what we'll see in this next example. So a manufacturing process produces wooden boxes, and it's vital to monitor the dimensions of these boxes to maintain quality standards. Each sample consists of 4 randomly selected units. So my sample size is 4, and I have 8 samples. Okay. The difference here, I've not only given you the averages, I've also given you the range, but I've also given you every single individual unit. Now, the only thing we need those individual units for would be to find the average and the range. But since you already have it, guys, I want you to ignore them. Don't get sucked into that. The only thing you would use, let's say you were missing a range, you can take the highest and the lowest and find the range. But that's all you need, again, those individual data points for. Now, we want to measure if this process is in control. It's a quantitative thing because we're looking at inches, we're looking at a quantity. So we need Xbar-R, which is the average of the averages. We need R-bar, which is the average of the ranges. So let's start there. So right now I'm adding up all my averages. Okay, I get 10.266. And then for the R bar, I get 0.3. Okay, super. So now for the control chart, the first one is X bar plus or minus A2 multiplied by R bar. Now, A2 is just a factor. This would be found in a table that's provided to you. You have it at the very end of this of the document. So if you go here, this is how you use this table. First, you go down to your sample size, and we had a sample size of 4. Don't use 8. Here's where you want to be careful, guys. Don't use the number of samples. Use the actual sample size, and then you have everything you need. So we're going to actually need all of these. We'll need D3 and D4 as well for something else. So what's going on here? Okay, so I'm going to grab this little clip of the table. Okay. So A2, D3, D4. Don't worry, these numbers are meaningless on their own. You don't have to interpret them. They're just factors. So Xbar-R is 10.266. A2 is 0.73. R-bar is 0.3. That's it. So there you have it. This is your control chart. So the next thing would be to figure out, like we did before, are all of your X bars within this limit, within these limits? So let's look. Anything below 10.1? No. Anything above 10.4? No. Okay. So the means are in control. But you can't say that the whole process is in control yet, because remember what I was saying. If you don't know the standard deviation, you need to test if the mean is in control, which now we know that it is, but you also have to test if the range is in control. It's not enough to just do one. Imagine this has to pass two tests. It passed the first one, now let's do the second one. For the ranges, the lower control limit is found by taking D3 multiplied by R bar, and the upper control limit is D4 multiplied by R bar. Okay, that's your UCL, that's your LCL, lower control limit, upper control limit. And you've got all of those right there in the table. You find these factors in the same way. Now, because D3 is 0, that one's easy. It's just 0. D4 is 2.28 multiplied by the average range, which is 0.3. So my limits are 0 and 0.684. So any range within this, range is normal. Are we good here? We're good. Everything within that limit. So we can say that the entire process is actually in control. The mean is in control. The range is in control. All of the variation is random, which is good. So nothing to investigate.